Okay, so I really enjoyed Graham's presentation. I'm going to take a different tack. You know me, I'm Mr. Technical. And what I want to look at today specifically is plyometric activity. As Graham quite rightly said, it's the core to not only high jump training, but a lot of athletic training, a lot of sports training. It has to be done well. I've seen plyometric activity which at best can be described as questionable and inappropriate. And I want to share my thoughts today on how I feel you should safely develop it. What I'm not going to give you is how many reps and how many sets. I'm happy to discuss my thoughts on those with you afterwards, but I want to look at the principles and the considerations that you should think about when you're building a plyometric program. Best thing to do, I think, is to start with a definition. If we understand what plyometric activity is, it empowers us better to use it. To me, there are three key elements. I've underlined the appropriate words: fast, explosive, and immediate. Plyometric activity essentially is an eccentric or a lengthening contraction of muscle, as quickly as possible, followed by a concentric shortening action of that muscle. Immediately being the key word. The longer the gap between the eccentric and the concentric, the more energy, potential energy, leaks away. The stretch shortening cycle becomes less effective. And that raises the question, perhaps, which we'll look at later: what activities really are plyometric, even though they contain eccentric, isometric and concentric activity? How are they linked and structured to be effective in the training process? Let's ask the question, is it plyometric? We all do drills, hopefully, component exercises. They can have a plyometric component within them. Is running plyometric? Bounding? Of course bounding's plyometric. We say hopping, working over hurdles, boxes, jump takeoff activity. Weight training exercises, is there a plyometric component in them, or can there be, which can enhance the training process? Remember the principle: there has to be an eccentric component, an isometric component, and a linked concentric component. Today we're looking specifically at high jump. So if we think of what are the desirable traits we want to see within the takeoff in terms of a good technical model. We generate energy for the takeoff through our contact with the ground. That's the only time we can do that. A stable base of full foot contact is imperative. What we actually see is contact times between 1300ths and 20 to 1 2200ths of a second. Long jump, triple jump, they haven't got that luxury. It's between 10 and 1100ths, or it doesn't work. We can actually be successful at either ends of the spectrum, and I'll give you a couple of examples in a moment. There has to be active use of the posterior chain muscles. That's the glutes, the hamstrings, the calf muscles. We should see a minimal bending of the plant leg. If we get to this position, are we going to be effective? And how does that impinge upon the plyometric activity that happens at takeoff? In addition to having minimal bending of the knee, we want no lateral displacement. So there has to be pelvic midsection trunk stability. You know, the buzzword core stability. It's not just the abs, it's the whole corset that wraps around the midsection. So as a coaching point, I haven't put core, I put midsection. If the midsection is tight and strong and stable, the transmission of forces is far more effective. So these are the coaching points, these are the cues that we have to be looking for in a quality takeoff. Know your athlete. I said we have this variability. Sotomayor, he's at the slower end of the spectrum. 2100ths, I think that was 1900ths on this jump at 241. Kostadinova still has the world record after 20 odd years, 1300ths of a second. The interesting thing is with Kostadinova, and again we're talking about holding the abs tight. If we actually just look at the shorts, coming to plant, how stable. You still see this fractional distortion through the forces and stresses at takeoff. This lady is running in faster than most British men. The forces at takeoff are phenomenal, yet she's able to control them, one through technical position, secondly through superb conditioning. So let's look at the takeoff mechanism in the high jump. In fact, any one-legged takeoff, one running takeoff, has an eccentric phase, an isometric phase, and a concentric phase. Okay, technical words, use them or not, the choice is yours, but if you see them in literature, it helps you to understand what's actually happening. The takeoff, and again, if those of you seen Donald Thomas, everybody goes, what a horrible technique. I've got video of Thomas. If you freeze him at the point of contact with the ground, he displays the same characteristics as everybody else. If you freeze frame him at the point he leaves the ground, he displays the same or similar characteristics as everybody else. What happens in between is also very similar. Foot was a bit unstable, now it's become more stable. He's obviously addressed that issue that injured him badly a couple of years ago. The idiosyncrasies that precede and the consequences that follow are individual, but he doesn't break the rules of good high jump takeoff technique. The eccentric phase begins the moment the foot hits the ground. You're running in at 7.5, 8 meters per second. You're trying to convert that to 4 meters per second vertically. There has to be a braking effect for that conversion to take place. So this is where the huge stresses impact on the body. The eccentric phase ends when the knee stops flexing. This is the point where the peak forces impact on the body. We want that time to be as short as possible. We want it to be instantaneous, but for it to be instantaneous is perhaps an over-expectation. But the longer it is, and this can be long in the untrained athlete or the young athlete, this is where the problems will occur, where the takeoff will become less effective or be an effective one. The final phase is the extension, where you go from maximum knee bend to the point at which you leave the ground. And if we actually look here, an example of Silnov, the Olympic champion, look at the angle change of the plant leg because of the forces. Not a huge amount of bend and forceful vertical extension at the end. If you actually look at the numbers, he plants with an athletically straight leg, or as close to athletically straight. It's not locked, it's a controlled straight leg position. Almost 180 degrees. The period of maximum flexion is, if we do the maths, 18 degrees of flexion. Is that right? Am I right, dearie? Okay, so it's not a huge amount. Running in at 8 meters per second, one of the consequences in this particular jump of the pressures have been transmitted through to the foot. And there's a slight foot instability here because the technical performance of the plant wasn't perfect. Some athletes will bend the knees more than this, but this has implications for what we're trying to achieve with plyometrics. If we look at a force trace of what's actually happening underneath the athlete's foot, the point he hits the ground, we see a spike very, very quickly, a few hundredths of a second into the contact time, as the heel hits the ground and he transfers onto the full foot. This part of the trace is the eccentric contraction, and you can see the loading building up onto the body. And this is the concentric, the extension. 3 examples here. A big spike at the beginning means the athlete slapped his foot in. It's not an efficient takeoff. Huge loading then detracts from the quality of what happens here. If you can get down onto a strong plant position quickly, minimize that deceleration, you can develop more peak power through the takeoff. And often we as coaches do a lot of short approach work because the body is able to actually tolerate more short approach takeoffs. It's easier to get into a good eccentric loaded position and then get a powerful takeoff. We can almost minimize the spike. The trick to aim for is to get this trace on a full run-up. Very, very difficult, almost impossible to achieve, but that's where we're trying to actually go. So that's a little bit of science and technology.